In the race to build safer autonomous systems, one challenge remains stubbornly persistent. How do you test AI when the real-world conditions it must handle are rare, unpredictable, or even dangerous? Imagine training a self-driving car to navigate through a blizzard, or detecting pedestrians in pitch-black nighttime streets. These are not hypotheticals. They're real-world edge cases that could mean the difference between safety and catastrophe. But collecting enough real data to train and evaluate AI under such conditions? Nearly impossible. You can't wait for a snowstorm to happen in the test corridor. And even if you do, the data is scarce, expensive, and risky to gather. So what's the answer? Synthetic data. Specifically, synthetic environmental augmentations. Images artificially transformed to simulate fog, rain, snow, and nighttime. But here's the catch. It's not enough to just generate these images. They have to be realistic. If the synthetic fog looks like a Photoshop filter, or the simulated rain doesn't reflect on wet asphalt, then any evaluation based on those images is meaningless. The AI might pass the test, but fail in the real world. This is the simulation to reality gap, a well-documented problem in AI evaluation. Synthetic data has long been used in training, but when it comes to testing, realism is non-negotiable. Today, we're going to dive deep into a new framework for evaluating that realism. Specifically, how well modern generative AI models can simulate adverse environmental conditions in car-mounted camera images. We'll compare two approaches: traditional rule-based augmentation libraries, like imgaug and albumentations, and modern generative AI image editing models, including OpenAI's GPT-Image-1, Google's Gemini 2.5 Pro, Alibaba's Qwen Image Edit Plus, and Black Forest Labs' Flux context. And we're not just relying on gut feeling. We're using two independent, automated metrics: a vision language model jury for perceptual realism, and embedding-based distributional analysis to measure statistical similarity to real adverse condition imagery. Let's start with the setup. We took 40 clear-day images from the ACDC dataset, driving scenes captured under ideal weather. These served as our consistent baseline. Then we applied the same 4 environmental transformations to each: fog, rain, snow, and nighttime. Each method, rule-based and generative, was given the same natural language prompt. For example, transform this image to show heavy rain with wet road surfaces. No prompt engineering tricks. No hand tuning. Just a fair, consistent test. Now, how do we judge realism? First, we used a 3-model VLM jury: GPT-4o, Claude Sonnet 4, and Gemini 2.5 Pro. Each judge evaluated the augmented image alongside the original, answering 2 questions. 1. Does the image convincingly depict the target condition? 2. Are the objects, spatial relationships, and scene semantics preserved? No scalars. No 5-point ratings. Just binary accept-reject decisions. Why? Because recent research shows that when LLMs assign scores on Likert scales, they suffer from calibration problems, scale collapse, round number bias, and poor discriminative power. Binary pointwise decisions, on the other hand, are more robust to manipulation and avoid the biases inherent in pairwise comparisons. We aggregated the results across all 3 judges to compute mean acceptance rates, a reliable, scalable measure of perceptual realism. But we didn't stop there. To validate these perceptual judgments, we ran a second independent test: embedding-based distributional analysis. We used 2 powerful vision encoders: CLIP, trained on image-text pairs, and DINOV3, trained through self-supervised learning. These models extract high-dimensional embeddings that capture semantic and visual features. For each condition, fog, rain, snow, night, we built a reference distribution using real adverse condition images from ACDC. Then we measured how close each synthetic image was to that distribution using a relative Mahalanobis distance. This metric is key. It subtracts the background similarity, shared features like road layout, object positions, to focus only on the condition-specific differences. That way, we're not fooled by the fact that synthetic images still look like the original scene. They're only supposed to change the weather. And we report the negated relative distance, so higher values mean better realism. Now here's where it gets interesting. The results are clear. Generative AI methods dramatically outperform rule-based approaches. The best generative model, Qwen, achieved a 94.8% acceptance rate on the VLM jury. The best rule-based method, imgaug, managed only 26.3%. That's a 3.6 times improvement. Even the weakest generative model, Flux, outperformed the best rule-based method by over 200%. And this pattern holds across both evaluation methods. In clip embedding space, the best generative method, OpenAI, was 4.3 times closer to real adverse condition distributions than the best rule-based method. So why the gap? Because rule-based methods are fundamentally limited. They rely on handcrafted heuristics: brightness reduction for fog, gamma adjustments for night, Gaussian noise for rain. These are fast and predictable, but they can't capture the context-dependent physics of real weather. Fog isn't just a gray filter. It's depth-dependent, volumetric, with light scattering that varies across surfaces. Rain isn't just streaks. It's reflections on wet asphalt, splash patterns, and droplets that interact with the environment. And snow. It accumulates on surfaces, falls in patterns, and changes the texture of everything it touches. Rule-based libraries simply can't model these complexities. They produce visually artificial effects, uniform filters, flat overlays, unnatural textures. But generative models, they're trained on massive datasets of real-world images and captions. They understand the relationship between weather and visual appearance. They know that a rainy road should reflect headlights, that snow should pile on rooftops and sidewalks, that night should bring darkness, but not total obscurity. That visibility should degrade with distance, not uniformly. And when they fail, it's not because the weather looks fake. It's because they change the scene. Our failure mode analysis revealed a fundamental trade-off. Rule-based methods preserve semantics perfectly, objects stay where they are, but their weather effects are obviously artificial. 97.5% of imgaug's rejections were due to realism alone. Generative models, on the other hand, often alter the scene, removing or distorting objects, while producing visually convincing weather. For OpenAI and Qwen, over 70% of failures were semantic, not perceptual. So you can't have both. Either your data looks real but changes the scene, or it preserves the scene but looks fake. For safety-critical evaluation, where both fidelity and realism matter, Qwen and Gemini emerge as the best balance. High acceptance rates, low semantic failure rates. Now here's a twist. The real-world baseline isn't perfect. Even genuine adverse condition images don't achieve 100% acceptance. Rain images were accepted at 93.3%, snow at 91.7%. Why? Because real-world conditions are ambiguous. Light rain, patchy snow, early morning fog. These are subtle borderline cases. So when a synthetic method matches or even exceeds that baseline, like Qwen on rain or Flux on snow, it's not just good. It's better than the real thing. But here's where things get even more nuanced. The metrics disagree. OpenAI's augmentations achieve the lowest clip distance. They're statistically closest to real adverse condition imagery. But they rank third in perceptual realism, behind Qwen and Gemini. Similarly, Flux's nighttime augmentations show moderate embedding distances, yet only 17.6% acceptance. This divergence tells us something important. Distributional similarity does not equal perceptual realism. An image might occupy the right region in semantic space, but still have artifacts, inconsistent lighting, or unnatural textures that a human-like vision model instantly flags. And conversely, a synthetic image might look convincingly real, yet be statistically distant from real data. Why? Because realism isn't just about statistics. It's about context. Take nighttime. All generative models produce outputs that are 65 to 110 times farther from the real distribution than genuine night images. Yet Qwen and Gemini achieve 95.8% acceptance, almost perfect. Why? Because the embedding models, CLIP and DINAV3, are dominated by global luminance and color statistics. They see darkness and assume it's night. But they don't care if the streetlights are in the wrong place, or if the car's headlights are missing, or if the road is completely invisible. A human judge, however, knows that nighttime driving requires visibility. You need to see the road, the signs, the other vehicles. So the embedding model fails here, not because the augmentation is bad, but because the metric is too narrow. This is a critical insight. No single metric is perfect. But when both metrics agree, like in fog, where both VLM jury and embedding analysis show clear superiority of generative models, we can be confident in the conclusion. And when they disagree, we trust the VLM jury more. Our qualitative analysis of the most divergent cases confirms it. Images that are statistically similar but visually flawed, like blue-shifted overcast scenes mistaken for rain, are correctly rejected. Images that are statistically distant but perceptually realistic, like Qwen's nighttime scenes with proper lighting, are accepted. So what's the takeaway? For safety-critical evaluation, rule-based augmentation libraries are insufficient. They're fast and predictable, but not realistic enough. Generative AI image editing models are the future, especially when used with a multi-metric evaluation framework. But we're not done. We still need human validation. Automated evaluation is scalable, repeatable, and powerful, but it's not a replacement for human judgment. The next step, directly comparing these automated metrics to human annotators. And we must extend this framework to other domains and datasets, different sensors, different geographies, different failure modes. Because as AI systems become more embedded in our lives, autonomous vehicles, medical diagnostics, industrial safety, the need for scalable, reliable evaluation is no longer optional. It's essential. So if you're building evaluation pipelines for safety-critical AI, here's the bottom line. Use generative AI for environmental augmentation. Evaluate realism with both VLM jury and embedding-based analysis. Trust the VLM jury when metrics disagree. Treat real-world baselines as practical ceilings, not perfect gold standards. And always be aware of the trade-off between realism and semantic fidelity. Because in the end, the goal isn't just to generate images. It's to generate meaningful tests. And that's what this research gives us, a scalable, principled, and powerful way to do just that. The future of AI evaluation isn't just automated. It's intelligent. And it's here.